Okay, so in this video I'm going to talk about sine and cosine series and how we are going to deal with these functions from within Fourier series coefficients and Fourier series in general. Okay, now let's go and start with the some definition related to sine and cosine series first. Okay, so first of all, if we are going to have a function called f, and this function is piecewise continuous. I think that you fully understand now what is the meaning of these two words. If you do not understand it, please revisit the previous video. Okay, so it is piecewise continuous. This is our function between minus L to L. So we are talking about function that is between minus L and L, a function that is crossing zero. Okay, something like this, for example. Okay, we can represent this function, which is f of x, at all but possibly finitely many points on minus L to L on this interval by its Fourier series. Okay, so this means simply we are going to represent it by Fourier series if it is piecewise continuous. Okay, simply. Okay, this series may contain just sine terms, just cosine terms, or both sine and cosine terms, because when we are going to give or make the Fourier series expansion for this function, it might happen that we are having like sine terms only or cosine terms only, or maybe both of them. Okay, so we have no control of this. Okay, so this is like something we do not control it. But if this function is defined on the half interval from 0 to L, if we are talking about this interval from 0 to L, okay, we can write a Fourier cosine series containing just cosine terms and a Fourier sine series containing just sine terms for this function on the interval 0 to L. Okay, understand? So the point is, if we are interested in half of the interval, which is this part of the function, then we can use cosine, okay, cosine, Fourier cosine series only, or maybe sine terms only to represent this part of the function. The condition is what? Exactly, this is the condition. From 0 to L, we're talking about from 0 to L. Remember again that our function should be piecewise continuous. Okay, piecewise continuous. Okay, now let's start with how we can obtain this. How we can obtain only cosine terms for a piecewise continuous function on the interval from 0 to L. Okay, we are going to put this in this simple form. Okay, so based on what we have discussed, we can define Fourier cosine coefficients. Now I'm talking about coefficients, okay, and we are talking about cosine, not sine, okay, of the interval from 0 to L, okay, from 0 to L, to be the numbers. These are going to be the coefficient, okay, it is going to be numbers. An equals to 2 over L. The integration from 0 to L, take care of the integration limits now. It's not minus L here, it is 0, okay? As we said, we're talking about half of the interval. Half of the, I mean that the function that supposedly defined from minus L to L, okay? So half of, from the integration from 0 to L, the function itself, f of x, cosine n pi x over L, okay? Cosine n pi x over L. So what is n? N, it is an integer taking 0, 1, 2, 3, or whatever, okay? And pi, constant. L, it is the interval limit, which is this one, okay? And then this is f of x, which is the function that we have, dx. The Fourier cosine series for this function on this interval from 0 to L is the series is going to be like this. Half a node, okay, and then a node which is related to 0 at the beginning, and then we are going to have the summation of cosine terms. What are these summation? we are going to start from n equal to 1 till whatever number that we want, infinity, and we are going to sum them up, and they are going to contain a coefficient called an, which is going to take 1, 2, 3, 4, whatever number that we want, okay, times cosine n pi x over L. Okay, so this is the definition now. As you can see from here, we have what? Two terms. I mean that basically two terms. One term is constant and a bunch of terms here, I assume them like one term, for example, that is related to cosine. There are many terms actually, but here they are, all of them, they are containing what? Exactly, cosine. Only cosine terms. Okay, in which an, which is the an's or these kind of coefficients are the Fourier cosine coefficients of the function on this interval from 0 to L. From 0 to L. Okay, great. I think that we have understood now what we want. Let's clean everything up. Simply, we are telling if we have a piecewise function on this interval, we can define it using Fourier cosine terms only using this equation. This is the simple terms what we want to do. Okay, using only cosine terms. Okay, now let's go to the convergence theorem. We want to know what is the convergence of Fourier cosine series when we are using cosine only. Okay, so if we are going to say that our function is piecewise smooth, as we said before, on this interval 0L, 0 to L means that if we have the function like this, so we are talking about something like it is piecewise continuous on from 0 to L, for example, then first of all, inside the interval, which is from 0 to L, when x between 0 and L, okay, the Fourier cosine series for this function on this interval converges to what? Exactly. I think that we are expecting it, right? It is going to be half of the function, which is f of x from the right. This means from the right, plus the function of the same x but from the left, right? Half of them. So as if we're taking the average, then you're going to find that it converges to what? Exactly, f of x, as we are going to see in the example and as we have done before in the previous videos. Okay, now remember that this is in between. Okay, but what about the convergence at the ends here, at 0 and at L? Here this is at 0, right? And here it is at L, at the ends of the interval. How we are going to see it? Then it is very clear for us here at 0, which is the beginning of the interval here, this cosine series converges to what? Exactly, the function, and substituted with 0 in this function from the right. And if we're talking about the other limit, which is L, so at this L, this cosine series converges to what? Exactly, the same function, but substitute with L, and this is going to be from the left, as if that we are approaching it from here. This is from the left, and here we are approaching here from here. Okay, so this is the meaning of the minus and positive that we are talking about here. Okay, now I think that we are ready now to solve an example and understand it more and implement what we have understood till now. Okay, now let's go to this example. Let f of x equals to e to the power 2x. This is our function. Okay, without thinking too much, if you want to check it, this is piecewise smooth, right? Piecewise smooth, and smooth because the derivation of it also is going to be piecewise, right? As we have explained before. Okay, now we want this function e raised to 2x for this interval. Take care that we have equal interval. I mean that equal sign here. This means that x is going to be between 0 and 1, and also it takes 0 and takes 1 here. Okay, we will write the cosine expansion. We want the cosine expansion, means that we do not want to see anything except cosine terms and the expansion of the Fourier series of f on this interval from 0 to 1. The coefficients are a node that we are going to start with, as we have mentioned before. It is going to be 2 over L. Let's go here and go back and check a node 2 over L, right? From 0 to L, f of x cosine n pi x over L, right? So now let's apply this. A node 2 over L. L here is 1, right? This is L. So the integration from 0 to 1, the function itself, okay, e raised to the power 2x, okay? That's the function that we are going to have here, okay? This is the first function that, or the first coefficient that we are going to have. And this is a limited integration, right? It is a limited integration. Limited integration means what? What is the meaning of limited integration? It means that we can, with these limits, we can, after integration, we can substitute and get the value of the integration directly. It's e squared minus 1. E squared minus 1. Okay, so this is here first, the first term, or the first coefficient that we are going to have 2 over L from 0 to L, f of x cosine n pi x. Here this is going to be 1 in our case, right? Because it is going to be cosine 0, right? So this is going to be 1, and we are having f of x times dx directly, right? Okay, so here as if that we are having 1, and then we are obtaining the value here. So this is a node. This is going to be like the constant term in our Fourier expansion. Okay, what about for n starting from 1 here? Okay, this is where that n equal to 0. Now we're starting with n equal to 1. Okay, so this means that an going to be 2 over L also, 2 over 1 from 0 to 1, e raised to 2x cosine n pi x over L, which is over 1. Right here, cosine n pi x over L. Okay, it is going to be, we are going to count it, and we are going to consider it. Okay, so in this case we are going to look to the integration that we have. Okay, it is as if that we are having two functions multiplied to one another. Then integration by parts can yield for us this fraction that you can see it here. It is one term containing exponential function and cosine function, and the second is exponential function also times a cosine. Okay, so commonly in this case we are going to realize easily that this term is going to vanish, right? Because it is going to be sine pi something, in 1, 2, if n takes 1, 2, 3 or something, it is pi here. So this means that we are talking about 0. So this would vanish, and then we are going to end up with 4e 2x cosine n pi x over 4 plus n squared pi squared from 0 to 1. Limited integration. I think that you can do it very easily, and we can end up with e squared minus 1. Remember, this is minus 1 always whenever we have cosine n pi x, and I have explained it before. Okay, we're going to end up with this minus 1 over 4 plus n squared pi squared. Okay, so this is our an terms. This is going to be our an terms. Okay, so now let's go and understand this more. Let's put our function. Now we obtained a node and an, right? We want both of them in order to put our expansion, the function or the Fourier series expansion. So the cosine series here, this means that the Fourier cosine series of the function, which is e raised to the power 2x on the interval that is 0 to 1, right, is going to be like this. Half e squared minus 1, this is the constant term that already we have obtained before, plus many terms from n equal to 1 to whatever type number or whatever number that we want to infinity of many multiplication of cosine n pi x. So these are the cosine terms here. Okay, so this is what we have already obtained before. This is what we have obtained before. This is an, right? Cosine n pi x. Okay, that's very good now. And now we are ready to plot it. Let's plot it and let's see the convergence even. Okay, so first of all, we have the series convergence. Converge to, we have, as we said, the from 0 to 1. This is the limit that we are having here from 0 to 1. Without thinking too much, exactly, it will converge to what? The function itself, which is f of x, right? And our function is going to be e to 2x. And if we are going to look to the first of the interval at 0, then we are going to find when x equal to 0, our function is going to equal what? Exactly, e raised to the power 2 times 0. So it gives us 1, right? And this is one limit, because as we said, it is f of x from, this is x from right here, as if that we are reaching here, right? So this is f of x from the right, approaching it from right, as if that we are substituting with 1. Okay, and approaching to 1 means that approaching to the function, okay, from the left, right? This is, sorry, I mean the left, this is the left, approaching to the, so approaching here to this one from the left means that f of what? E raised to the power 2 times 1. So how much? Yes, e squared, it will be e squared. So this means at 1, we're going to end up with, exactly, as you can see, e squared. That's right, between 6 and 7 almost, right? So this is the function for us now. Let's see it clearer here. So this is the figure. This is the fifth partial sum, means that we are taking, like in here, we're taking it like five terms of the cosine series in this example. So we can find, look here, this jagged line here that is going back and forth, something like this is the Fourier series. This is the Fourier series. And the other one, the smooth one, this is the function itself. So we can see that almost Fourier series is representing our function in a perfect way. Okay, this is the fifth partial sum. If we take a tenth, then you're going to find them almost the same. Okay, so as we can see here, the Fourier series converges to e squared when we are talking about f of x from the left at L, okay, and it converges here to f of x from the right when our limit is going to be 0. Okay, these are the limits that we have at 0 and 1. So this is the Fourier series. As we said, it converges to e raised to the power 2x for x between 0 to 1, and the figure even including here, because this is right in this case, we are going to find that it equals at the ends e to the power 0 and e to the power 1. So it is okay. Okay, so I hope that you understood it well. This is the end of this cosine Fourier series and the convergence and one example on it. Thank you, and see you in the next video.